In this video, we're going to look at working backwards. We're going to start with the derivative and figure out what that derivative tells us about the original function. And so this goes to certain objectives that go with the course. We need to know that the derivative can be represented graphically, numerically, analytically, and verbally. Okay, today it's going to be graphically mostly. We'll know that the first and second derivatives of a function can provide information about the function and its graph, including intervals of increase and decreasing, local, relative, and global extrema, maxes and mins, intervals of upward or downward concavity, and points of inflection. And we'll also know that key features of functions and their derivatives can be identified and related to their graphical, numerical, and analytical representations. And again, we're going to deal mostly with graphical today. Okay. So, say we're given a derivative and we want to know something about the original function. And there are a lot of applications of calculus that depend on our ability to figure out a function f from information concerning its derivative. Now, something that we know working backwards, we know this already. Now we're gonna start from the other end though. If f prime of x is greater than 0, so it's positive, then f is increasing. Now we've done that the other way. We've done that if f is increasing, the derivative is positive, but it's a two-way street. So you can probably guess the next part. If it's less than 0, so it's negative, then f is decreasing. We know that if f prime equals 0, there is a potential max, min, or flat spot. We don't know what's there until we do a little more analysis of the derivative. Okay. Now, so let's look at now, what does the second derivative tell us about a function? Well, if we go back here a little bit and we draw a function such as this one, the first derivative is would reveal spots. It's increasing, it's decreasing, it's increasing. The second derivative can tell us about concavity. This area from here to about here, this is concave down, whereas this section from here on is concave up. And it does tell us something about both the derivative and the original function when we know concavity. Okay? The second derivative, so if the second derivative, f double prime, another way of saying it, f double prime of f, is positive, it's greater than 0, then f is concave up. And along those lines, then, if f double prime is negative, then f is concave down. And again, this is a two-way street. It's a two-way street. So if the second derivative equals 0, there is a potential inflection point. In our drawing up here, this is an inflection point, which is a change in concavity. Okay. Now those inflection points would also be important for the derivative for f prime, because f double prime is the derivative of f prime. Okay. And of course we have to do more analyzation before we would know whether there was an actual inflection point at there or not. Okay. All right. What inflection points tell us about a function? Now, inflection points do, as we just pointed out, they tell us about changes in concavity. Concave up to concave down, or vice versa. But they can also tell us that it can be where the function's rate of change often, not always, reaches a maximum or minimum at points of inflection. Okay. And so we should look for that. Now let's summarize what we have here. We have f, and f prime, and then we have f double prime. Okay. So if this is positive, then f is increasing. If this is negative, then f is decreasing. If there is a maximum, then f prime is 0, and the changes from positive to negative. So it changes, so the function should change from increasing to decreasing. That makes sense. For maximum, it was increasing, and then it changes to decreasing. A minimum would also be 0, or in some cases does not exist. Okay, we don't have that very as often as it equals 0, but it could be, and the derivative changes from negative to positive at that point. Now, we also could have a flat spot or a terrace point. Okay, be 0, and there's no sign change. There's no sign change there. Okay. If our graph is concave up, then the second derivative is positive. Okay. If it is concave down, okay, and then the second derivative would be negative there. If it has an inflection point, okay, then the second derivative will be 0, and there may be a change of sign. There's a change of sign. If there's no change of sign, then there's no change in concavity. Okay, but it have to have a 0 and a change of sign. So that's the table that we're going to need. And notice we could also put this as f prime and this f double prime, and all these things would be true. In other words, if the second derivative is positive, then the first derivative is increasing. Let's look at Alright, the graphs below sketch the graph of f of x given f prime. The graphs below represent derivatives of two functions. Sketch the original function is what we want to do here. So this is a derivative. This is f prime, we're going to call it, and this is another f prime. So now I want to sketch the original function. So now instead of dividing it by the maxes and mins, now we divide up this by the zeros. There's a 0 here and a 0 here, because important things happen when the derivative is equal to 0. Important things happen when the derivative is equal to 0. And so if we divide it up here, in this area f prime is positive. In between here f prime is negative, and back here f prime is positive again. Okay? Which means my original function must be increasing. And then here my original function must be decreasing, and then here it's increasing again. Okay, so if we want to draw that, then we need to, our function needs to be increasing at all times, and it should have a, since it's changing from increasing to decreasing, there's going to be a maximum here, and there's going to be a minimum here, because it's going to change from decreasing to increasing. So if I'm marking those spots right here, I bring this down right about here, and then right about here. On this line somewhere there's going to be a maximum. We don't know the shape because we don't know. We'd need to know a little more information if we wanted to have a exact graph, but our graph will be a sketch that could be used, so used just in general. Now halfway in between here at this there's a minimum. At this minimum, okay, we can talk about different things that are going to happen there as well. Okay, alright, so let's pick, there's going to be a maximum, and we don't know any information. If they give us a point, we could use that point, but we can't, so we just pick a point. That's going to be a maximum right there. Okay, there's our maximum point. And the graph, my original function is increasing until it gets to there, and then it's decreasing, not very much, it doesn't do it for very long, it decreases until it reaches a minimum. We'll put it right here, decreases until it gets to there, and then it's going to increase forever on then. Okay, and that would be a possible sketch of f. Now we can move it up, we can move it down. That's a possible sketch of f. Okay. Now let's look at this one, this f prime here. This one, it's always increasing. Well, no, it switches. There's a 0 here. 0 here. So in other words, this f prime is, if we divide it up here, f prime is negative, so f is decreasing, and over here f prime is positive, so f is increasing. So we're going to have a minimum value here. We're going to have a minimum value this time, because my derivative is in the negative, so my original function is going to be decreasing. So I'm going to pick a point right here. That's going to be my minimum value. And so f's going to be decreasing till it gets to here, and then it's going to switch to increasing. Okay. Increasing. Something like that would be potentially be an antiderivative, as it's called. Okay. Speaking of antiderivatives, okay, an antiderivative is a function f, an antiderivative of f, we should say, function f such that f prime, capital F prime, equals little f. And those are going to become important as we go on. We'll spend more time on them later. But basically right now we are drawing antiderivatives, and later on we'll actually find some formulas for antiderivatives in the way that we find formulas for derivatives. We're not quite there yet. So this is an antiderivative. This is the antiderivative. This is an antiderivative. Okay. We're not going to do much else with antiderivatives right now. We want to know what they are. It's the opposite of taking a derivative. We take the derivative, the antiderivative, we get back to where we started. Good.